In this video, we'll be going over composite functions and how we find the domain of composite functions. So a composite function is when the output of one function is used as the input of another function. And so for any input x and functions f and g, this action defines a composite function. So this is how we write a composite function either way. How we read this is f of g of x. That's how we read this right here. And actually both of these are read like that. And then it says the domain of a composite function f of g is all x such that x is in the domain of g, and g of x is in the domain of f. So we'll talk more about the domain for a composite function later in the video. But first, let's talk about how we can evaluate a composite function. So what we have here is we have three depictions of two separate functions. And actually, why don't I number these so it's easier to follow along. All right, so using the following functions, evaluate a of g of 3, m of h of 1, f of a of 2, and g of m of 1. Okay, so we have 6 functions here. 2 of them, I guess this numbering doesn't make sense. 2 of them are written as equations. 2 of them are written in a table, and then we have 2 functions as graphs. So let's just go through. A circle g of 3. So a of g of 3. What this means is take the g function, evaluate it at 3, and then input it into the a function. So first of all, we want to find g of 3. G is this graph down here. So what we're going to do is at 3, we go to the y value, and that's -1. So we're going to say a g of 3 was equal to -1. So now we're going to say a of -1. The a function is up here, so I'm going to input -1 into that. I get -1 squared plus 1, and that gives me 2. So this is equal to 2. The next one says m of h of 1, which means m of h of 1. So I'm going to evaluate h of 1 first. H of 1, that's in the table. So I go the h function, and my input is 1. So I'm going to look at this value right here. So that's h of 1. H of 1 is equal to 1. So now I'm going to say, what is m of 1? The m function is also in the table. So I go down to an x value of 1. That's the input. And then m of 1 gives me 2. So this is also equal to 2. Next, we have f. I'm just going to write it like this right off the bat. F of a of 2. So a of 2. A of 2 is, let me clean this up a little bit. A of 2 is up here. So it's going to be 2 squared plus 1 is equal to 5. So now I'm going to have f of 5. F of a is equal to 5. So now the f function is this bottom right graph. So I'm going to go over to 5, and that maps to a y value of 2. So f of 5 is equal to 2. Wow, what a coincidence. They're all 2 so far. And then lastly, we have g of m of 1. So the m function of 1, we already found that. M of 1 is 2. So now I'm going to have g of 2. And g is in this graph. Let me erase a little. G of 2 is right here, and that is right on the y-axis, so that's 0 here. Okay, so in this example, we just saw how we can compose multiple functions or 2 functions together when they're given to us in different formats. Okay, the next example says, all right, we have these 2 functions, find each of the following. So we're going to do these compositions. So f of g of x. So I'm going to take the g function. That's the input here. I'm going to input that into the f function. So what this means is wherever I see x, I'm going to input this statement. So I have 3 times 5x plus 7 squared minus 1. That's fine. We can simplify this a little bit further. 5x plus 7 squared means 5x plus 7 times 5x plus 7, and then minus 1. So I'm going to go 5x times 5x is 25x squared. And then I have 7 times 5x is 35x. 5x times 7 is another 35x, so that's plus 70x. And then 7 times 7 is 49 minus 1. And then distributing this 3, I get 75x squared. 3 times 70 is plus 210x. 3 times 49 is 147. And then I have this minus 1 in the back, so minus 146. So that is f of g of x. And then for g of f of x, we just do the kind of the inverse. So what this means is we're going to take the f function now, and I'm going to input this. I'm going to input this right here for x. So it's going to be 5 times 3x squared minus 1 plus 7. So distributing that 5, I get 15x squared minus 5 plus 7. And then I can combine those constants, 15x squared plus 2. And that's it. All right, so that is how we compose functions. Now the next piece that we want to be able to do is find the domain of these functions when we do the composition. So these are a little bit tricky, so we'll take our time here. It says the domain of a composition is the intersection of the domain of the input and the composite function. So what we do is we look at the input function and we look at the resulting composition function, and we want to see where those domains intersect. So this first one says we have these two functions, f of x and g of x. We want to find f circle g, or the domain of f circle g, and then the domain of g circle f. Okay, so f circle g of x is f of g of x. So let's figure that out first. So I'm going to take the g function. I'm going to input it into the f function wherever I see the x. So this is going to be square root of 3 times 5 over x minus 1 minus 1. Now, to clean this up a little, multiplying the 3 by that fraction, I get 15 over x minus 1. To minus 1 from that fraction, I need to get a common denominator, so 1 times x minus 1 over x minus 1. So this comes out to minus x minus 1 over x minus 1, like this. Okay, and then combining these two fractions, well, the denominator of those two fractions is x minus 1. And then what I'm going to have is this negative right here makes that a negative x, and then I have a negative times a negative makes that plus, so 16 minus x over x minus 1. So that is the composite function. So what it says back up here, it says the domain of this function is the domain of this thing that I just found, intersected with the domain of the input. Well, what the function that we are inputting here was the g of x. So I also need to find the domain of g of x. So the domain of g of x, well, the domain of this rational function is just what makes the denominator 0. So x equals 1. So the domain for g of x is everything except for 1. So what I'm going to do is I'm going to put an open circle there. Then I'm going to shade all of this. So to find the intersection of two domains, I'm going to graph them both on a number line and see where they overlap. So I found the domain of the input function. That's this in blue, the domain of g of x. Now I need to find the domain of this thing down here of f of g of x. Okay, so let's just think about this. Well, I have a radical function, and I know that I can never have a radical function that has a radicand that is negative. So I know 16 minus x over x minus 1 must be greater than 0. Okay, and so how do we solve this? When is a radical function going to be greater than 0? Well, we can do this algebraically, but if we graph this graph looks something like this, and then like this, and it hits right here at 16. So what we see is, well, this graph is positive from 0 up to 16, but we don't include 16. So that is the domain there. So the domain of this, of f circle g of x, the domain of that is from 0 to 16. Okay, so if I graph this, the domain is from 0 to 16, and I'm not including those. Okay, so if I look at these two number lines together, where do they overlap? Well, oh, I made a slight mistake here. This domain from that graph doesn't go to 0. It goes to 1. So this is 1 to 16. So there's a vertical asymptote right here at 1. And that makes sense because in here I can't input 1, and anything less than 1 is going to give me a negative value. So let me see if I can clean this up a little. So I should have 1 right here. So my domain, when I look at the overlap of that, well, what part is shaded in both of these? Well, I start at 0 or at 1 on both of these, and then I go up to 16. The blue graph keeps going to the right, but because I stop on the black graph at 16, the domain, the part that's shaded in both of these, is 1 to 16. So what we'd say is the domain, I'm kind of cramming this in here, but the domain of f circle g of x is from 1 to 16, and that would be it. Okay, so we need to also do this next one. Let's see if I can add a page here. I want to go like this. I used to know how to do this. Let's see. We can just go down here. So the next question says, find the domain of g circle f of x, and our functions were f of x is equal to 3x minus 1 square rooted, 3x minus 1, and g of x was 5 over x minus 1. So now we're going the opposite direction. So now we want to find g of f of x. Okay, so I'm inputting the f function into the g function. So I'm inputting that in right here for x. So we get 5 over the square root, 3x minus 1, and then minus 1 here. And since the input function is f, I need to find the domain of f of x. The domain of f of x, well, because that is a radical function, I take the radicand, set it greater than or equal to 0, add 1 to both sides, divide by 3. So x has to be greater than or equal to 1/3. So if I put this on a number line, put 1/3 here. Since we're including it, we can put a closed circle there. So the domain for the input function is 1/3 and above. Now I want to find the domain of this thing right here. So when I have a rational function, when I have a fraction, what that means is the denominator cannot be 0. So what I'm going to do is I'm going to take that denominator and set it equal to 0 and see what I get. Well, add 1 to both sides, And then we're going to square both sides to get rid of the square root. 3x minus 1 is equal to 1. Add 1 to both sides, and then divide by 3. So what this is saying is x can be anything except for 2/3. So if I draw that on a number line, this is saying, well, it can be anything except for 2/3. Okay, so looking at both of those number lines, what part overlaps? Well, it looks like I can start at 1/3 on both of these. I'm not going to have 2/3, and then it goes all the way to infinity. So the combined domain here of G circle f of x is going to be, well, we're starting at 1/3, and we're going to include that. We go up to 2/3, and we don't include because we have an open circle, union, and then 2/3 to infinity. And that is the domain for that composite function. Okay, let's look at one more example of these composite functions here. All right, let f of x equal 5x minus 7 over 2x and g of x equals 7x plus 2. Find the domain of each set of compositions. Okay, so we'll do f circle g first. So f of g of x. So I'm taking the g function and I'm inputting it into the f function. So 5 times 7x plus 2 minus 7 over 2 times 7x plus 2. Okay, so this is a rational function. I want to know what is going to make that denominator 0. So all I do is I take the denominator, set it equal to 0. I can distribute the 2. I get 14x plus 4 is equal to 0. Subtract 4 from both sides. Divide by 14. I get negative 4/14, which is negative 2/7. So what this means is on a number line, x cannot be, let's put it over here, cannot be negative 2/7. But it can be any other value here. Okay, and then so that's the domain of the resulting composition function or composite function. And then the input function was g of x. So the domain of g of x, well, this is just a polynomial, which we love polynomials because the domain of a polynomial is all real numbers. So when I put these two together, I have these number lines are shaded everywhere except at negative 2/7. So the domain here for f circle g of x is negative infinity to negative 2/7. I don't include negative 2/7, union negative 2/7 to infinity. All right. And then this last one, now I'm going to go the opposite direction, g of f of x. So I'm going to take the f function right here, and I'm going to input it in for x. So we have 7 times that fraction, 5x minus 7 over 2, x plus 2. So when I multiply 7 by that fraction, the 7 just gets distributed to the numerator over 2x plus 2. So I want to know, when is this function undefined? Well, this function is only going to be undefined when that denominator is equal to 0. The only time that the denominator is equal to 0 is when x is 0. So x cannot be 0 here for that composition. So I'm going to put an open circle there, shade all of this. Okay. And then the input function was f of x. And looking at that input function, I have the same thing. That function is defined everywhere except when x is 0. That's the only thing that's going to make the denominator 0. So we have an open circle here. And then, okay, so those two number lines are the exact same. So the intersection should be pretty obvious. So the domain here of f, this was g circle f of x is going to be negative infinity to 0, union 0 to infinity.